Now we see some examples related to congruence modulo 3. Define a relation T on set of integers such as for all integers m and n, m is related to n if and only if 3 divides m minus n. Or we can write it also m is equal to, m is congruent to n mod 3. So this is the relation. This relation is called congruence modulo 3, and we need to check it that it is reflexive, symmetric or transitive. So now for reflexiveness we choose an m, a particular but arbitrarily chosen integer. Now we see here that m minus m is equal to 0 and 3 divides 0. So we can say that 3 divides m minus m, and hence by the definition every such pair will be present in the relation. So this is reflexive relation. So the T is reflexive relation. Now we check this example for symmetricness, that whether this relation is symmetric or not. So for this we need to show that if m is related to n, then n is related to m. We choose two integers, two arbitrary integers, and these integers also satisfy the condition, given condition, and related to each other. So we must show that n is also related to m. So by applying the definition on this on these two integers, we see that m is related to n means 3 divides m minus n, and by division, by the definition of division, we see that m minus n is equal to 3 into some integer. And now if we multiply both sides by minus 1, we will have n minus m is equal to 3 into minus k. And since minus k is an integer, this equation shows that 3 also divides n minus m. And hence this relation is symmetric. And for transitive property of the relation, we need to check here that if A is related to B and B is related to C, then if A is related to B and B is related to C, then A is related to C. Now suppose Mn and P are particular but arbitrarily chosen integers that satisfy the condition mtn and ntp. So, and we need to show that m is related to p. So by the definition of the relation T, since m is related to n and n is related to p, 3 divides m minus n and 3 also divides n minus p. So these are the two assumptions, and from these two assumptions we get two equations, which is m minus n is equal to 3r and n minus p is equal to 3s for some integers r and s from the definition of division. And now what we need to show is that A is related to C means M is related to P. We need to solve these equations simultaneously so that we get a relation between M and P. So for this we are adding these two equations, and by adding we get minus n is cancelled out with plus n, and 3 is taken as a common factor. So we get m minus p is equal to 3 into r plus s, where r plus s is an integer, and by the help of this equation we can see that 3 divides m minus p. So it also satisfies the given condition of a relation. So m is related to p, and since m and p are arbitrarily chosen integers, so it is true for all the integers m and p, and hence it is a transitive relation. Now we see here that relations can be combined, and since these relations are basically subset of a Cartesian product A cross B, so these also behave as a set. So set operations are valid on these relations. So given two relations R1 and R2 from set A to set B, then we can combine them, like we can take union of these two, and also we can take intersection, and we can also subtract them. So the resulting new relations will be some other relation from A to B. And there is another way to combine a relation, and we see here the definition. Let R be a relation from a set A to a set B, and then we have a relation S from set B to set C. The composite of R and S is the relation consisting of ordered pairs AC, where A belong to A and C belong to C, and for which there exists an element B, and this element is important, such that A is related to B in R and B is related to C in S. So we denote the composite of R and S by S composition R. So we are basically saying that if we have a set A and a set B, and here some element is present which is attached to an element of B in a given relation R, and then there is a set C and a relation S in which that element from B is attached with an element of C. So we can make a relation from set A to set C directly. So this is how a composition of two relations works. So R is taking an element from A to the set B, and S is taking that element to set C. So we have a relation from A to the set A to the set C. In other words, if relation R contains a pair AB and relation S contains a pair BC, then the composite of two relations will contain a pair AC, and that's how we can combine two relations. Now we have some examples of combining relations. So in the first example, we see that we have a relation D and a relation S on a set A, which is 1, 2, 3, 4. So A, B are related in D such that B is equal to 5 minus A, and S in S two elements are related whenever A is less than B. So now we pick elements from A which satisfy this relation, and now we see that 1 and 4 satisfies the relation, since 1 is equal to 4 is equal to 5 minus 1, and just like 3 is equal to 5 minus 2, and for 3 2 we have 2 is equal to 5 minus 3, and just like we have 1 is equal to 5 minus 4. So these are the elements in D, and for S we have to check the less than relation. So 1 is less than 2, 1 is also less than 3, and 1 is less than 4, and so on. We can also make this relation, and now we are taking composite of these two relations. So here in this relation which is composition of S and D, D is taking an element. So to understand this relation, we need to see that what are these properties and what is the role of B, which is present in both these relations. So we need to understand that D is mapping an element A to the element 5 minus A. So it takes A as an element and it gives us, and it associates it with an element 5 minus A. And afterwards S maps 5 minus A to all the elements which are larger than 5 minus A using the condition in S. So when we combine these two and take the composition of these two relations, what we get here is that A and B are related in the set A when 5 minus A is less than B. Or equivalently, we can solve it and we get that A plus B is greater than 5. So we are checking those elements in which the sum of these two elements will be greater than 5. So these will be not 1 and 2, not 1 and 3, and not 1 and 5, 4. It will be 2 and 4, and then we have 3 and 3,